Okay, so this lecture is going to start our series of lectures now that are going to look into the different process classifications for 3D printing or additive manufacturing. These are standardized classifications, so we're going to take them one at a time, going through each process and discuss the details of the process, how the processes work, and what are the major companies that are using these processes, and also the variations. There's a lot of variations within each one of these processes. So we're going to start off with this lecture talking about the Vat Photopolymerization class of 3D printing or additive manufacturing. Vat photopolymerization is a liquid-based process. Okay, so you can see in this diagram that there are three broad categories of additive manufacturing. We have liquid-based, solid-based, and powder-based processes. And liquid-based has three different processes under the liquid-based category: vat photopolymerization, material jetting, and material extrusion. And so we're going to be talking about that photopolymerization today, and we'll hit the other processes and different categories in subsequent lectures. So the vat photopolymerization process. The official standard definition of vat photopolymerization is it is an additive manufacturing process in which liquid photopolymer in a vat is selectively cured by light activated polymerization. And you can see in the figure on the right a generalized approach to this. We're going to go through each one of these parts of this process in the slide after it, but let's keep it kind of broad at this stage. The build material for the vat photopolymerization process is going to be a photopolymer, right? A photopolymer is a thermoset. Remember that there are two types of plastics. There's thermoplastics and thermosets. So a photopolymer is a thermoset. And basically a photopolymer is a special type of plastic that starts out in a liquid state, okay? And as you shine a light on it, either from a UV light source or from a laser, when you shine a light on it, that area that's hit by the area of the photopolymer liquid that's hit by the light, that's exposed to the light, will turn into a solid. Okay, so it has a liquid to solid transfer. The material distribution method in a vat photopolymerization process is the vat or the reservoir. So you need basically a big reservoir or container of the photopolymer, the liquid photopolymer, and then your part is going to build from that vat. And the binding technique, that is how we keep all the layers together and the other parts of the 3D print, is from a light source. Basically, it can be a UV light, it can be a laser. Any type of light is going to activate and bind the liquid into a solid so that we have our 3D printed object. Okay, the process for photopolymerization. Okay, so the steps are as follows. So the first step is the build platform is lowered from the top of the resin vat downward by the layer thickness. Okay, and by the way, I'm talking here about the basically the initial vat photopolymerization process, which is stereolithography. Okay, and in that process, the build platform, okay, started at the top of the reservoir of the photopolymer, and then the build platform was lowered by one layer thickness, okay, UV light cures the resin layer by layer. The platform continues the move downward, and additional layers are built on top of the previous layer. Okay, so in this example, in the SLA process, stereolithography process, the build platform is going to move down, and each new layer that's exposed on the build platform is going to be selectively cured by the light source. So building on the next, and the build platform is going to continue moving down. So, some machines use a blade, which moves between layers in order to provide a smooth resin base to build the next layer on. So the blade is going to move across the previously constructed layers, right? It's not going to move across the platform and sweep off the layers that are already solid, but it's going to move across the last built layer and just kind of smooth that off so that you have a good surface to build on. After completion, the vat is drained of resin and the object is removed. Now, I'll have videos to kind of show how that works, because I know that talking through that, it's a little bit hard to understand. The different vat photopolymerization technologies, that are out there include stereolithography, the SLA. This is the original 3D printing process, right? The one that was started by Charles Hull with 3D systems. Subsequently, there are many new SLA manufacturers out there because that patent has expired. Then there is the DLP, or digital light processing technology. And there's a lot of different major industrial manufacturers, including EnvisionTech, Prodways, Karima, Asiga. There's probably more. There's the 3SP process, which stands for scan, spin, and selectively photocure, and this is done by the EnvisionTech system. FTI, film transfer imaging, by 3D Systems again. And then one of the processes that has really taken hold and is quite popular right now is the CLIP process, continual liquid interface process, and that's been developed by the Carbon company, and I think that there are new similar technologies out there. But the three big ones right now are the SLA, DLP, and CLIP process. Okay, so some of the strengths of the vat photopolymerization process are it has excellent resolution, probably the best resolution and accuracy of any of the 3D printing technologies that are out there, any of the different processes, okay? It has extremely high resolution and accuracy. It has a very good surface finish. It can handle a range of different technologies so that there's different, you have DLP, SLA, CLIP, all the other ones. There's new ones out there as well. And it's a relatively quick process. Actually, the fastest known process right now, 3D printing process, is a vat photopolymerization technique. So it's very, very fast. Some of the weaknesses for vat photopolymerization are that it can have very brittle parts. Now they're working on this. This is kind of more of a material problem than it is of a process problem, but it does have some brittle parts. There are, however, some materials and some processes that have really fixed this process. So you might have heard of there are companies right now that 3D print shoes. And when I say they 3D print shoes, they don't actually print the whole thing, but they print the cushion under your footbed, so the part that you walk on. And some very expensive high-end running shoes have 3D printed insoles. And those are printed using the CLIP process, vat photopolymerization, CLIP technology by Carbon, and others at this point. And that really tells you right there that those shoes could not be made from brittle material if they were going to last for any length of time. So the brittle parts here kind of depends a lot on the material and maybe to a lesser extent the technologies. There is support removal required. So there are supports that are required on in this process, as we'll be talking about it, and they do require removal, manual removal, usually clipping with some kind of pliers or clippers. There is a solvent required for this. There is post-curing that is required. So there's post-processing here, finishing, so to speak. Parts can warp and twist. And then they are moisture and UV sensitive. Okay. Again, this is kind of material dependent, the moisture and UV sensitive nature of it. But depending on the material used, you will have to pay attention to that and watch that those weaknesses. Some notes about vat photopolymerization. Bioprinting uses vat photopolymerization process almost exclusively. All right. So, when you're, and we're not talking about building medical models. We're talking about actually bioprinting like, cells and organs and things like that. Okay. So it uses vat photopolymerization. There are two main, VP systems, right? There is the vector scan system, also known by the acronym VSVP, Vector Scan System. And that is what we use in the stereolithography process, okay? And then there is the Mask Projection System, MPVP, and that's what we use, or that's what's used in the digital light processing system, okay, or technology. The VSVP system laser traces an outline of the slice at each level. All right, and a scanning mirror is used to orient the laser along the path. All right, so the laser is not being moved, right? The laser itself, the body of the laser is not being moved, but the laser light is being redirected by using a scanning mirror. And a scanning mirror is basically a mirror that's attached to a servo. And the servo is a very fast motor, and the servo moves the mirror in such a way that the laser hitting the mirror is reflected onto the object, or into the liquid in this case, in exactly the outline that it needs to trace the path of the of each layer. Okay, the MPVP system, that is the mask projection system, is faster because you're polymerizing, solidifying the entire slice instantaneously. Okay, so in a vector scan system, the laser is tracing out the path, right? But the photopolymer is being cured only when the laser hits it. So only as the light from the laser hits the polymer is it going to solidify, right? So in the mask projection system, the light source is going to strike everything, the whole layer instantly. And so it cures in that whole flashing of the slice. All right. So that's why the MPVP system is a much faster system. It doesn't have to wait for the laser to trace out the whole path. All right. So we should also talk about the question of resolution versus accuracy, because the VP system is a very accurate and has high resolution. Not all systems have the same resolution and accuracy, or I should say, not all technologies, not all 3D printing or additive manufacturing processes. So when we talk about resolution, we're talking about the smallest movement the printer can make. Okay, so it's divided into basically two different directions, right? We have the XY plane movement, right? That's usually the plane that is parallel to the build platform. And then we have the the Z resolution, and that's the vertical resolution. And that's what gives us our layer thickness. Okay. And so the vertical resolution is the smallest movement the build plate or the print head can make in the Z direction. So there's two different things going on. The XY resolution, or the XY plane resolution, also known as the horizontal resolution, is the smallest is the smallest movement the printer can make in the XY plane. Usually these are different motors, okay? The horizontal resolution and the vertical resolution. And there's also different settings that can control, especially when we talk about the vertical resolution or the Z resolution, all right? When we talk about the units for each one of these different resolution categories, we can talk in different unit categories. So we may talk in inches or millimeters for some of the large scale printers. For some of the smaller printers, we often talk in microns or micrometers. That is a millionth of a meter, right? We can also, especially for the DLP process, we can talk about DPI or dots per inch or pixels per inch, PPI. Factors affecting the resolution include the laser diameter, right? The pixel size in terms of the DLP process, the particle size for powder-based processes, the nozzle diameter for material extrusion and some of the other extrusion-based processes, and also the STL triangle size or the mesh size. So there's a lot of factors that can affect resolution. And not all of these we can adjust. Some of them, such as powder size, nozzle diameter, laser diameter, you're kind of stuck with it, right? I suppose with a nozzle diameter, you could maybe change out your nozzle by a different print head, but for some of the print, for example, the material extrusion process, you usually have different filament diameters. And so, you have to match up your filament diameter with your nozzle diameter. All right. So, then we have the question of accuracy. Accuracy is the ability of the printer to move exactly as instructed. All right. So, we can have and I like these diagrams here because they kind of show this. The first one on the left is a process, or let's say we're throwing darts, Okay, so in the figure on the left-hand side, you can see an example of a not accurate and not repeatable process. So we have no accuracy, right? Remember, we're aiming for the bullseye, so the process data points are kind of all over the place, and it's not repeatable. That is to say, they're not clumping. Okay, so we need both in terms of the operation of a 3D printer. In the middle figure, we see an example of a 3D printer or a process that is repeatable. Okay, so we're getting clumping. So the process or the part or whatever is occurring the same way every time, but it's not occurring accurately every time. So, an example of this in 3D printing would be like printing the part off from the desired location, or having the layers kind of move in a cascading function that is not desirable, not accurate, but it's happening every time. And those problems, because these are problems, right? Those problems, the not accurate but very repeatable problems, kind of narrow down your options for solutions. So it's very good, as good as it can be in terms of a problem, to have a repeatable but not accurate problem. Okay, because you're kind of addressing, you're going to be looking for the problem that caused the lack of accuracy. And in the final figure, of course, we have the golden solution here, the very accurate and very repeatable process. That is to say, the data points are clumping around the intended target. Okay. So when we're talking about factors that affect the accuracy of a 3D printer, we can talk about the linear motion. Okay. All the 3D printers are going to have some type of linear motion involved in them, whether we're moving the print head, whether we're moving the mirror that the laser is going to be directed onto, whether we're moving the build platform up and down. Okay, so those are all linear motion factors, and we don't want any friction, or as little as possible, friction in the linear motion. If we have motion that is intended to be synchronous, we want to maintain that synchronicity, I should say. So we don't want one motion to be moving faster or slower than the other one. Another factor that affects accuracy is the actuators. The actuators are the motors that drive that linear motion. Okay. There's other motors that are on a 3D printer. So, for example, in the material extrusion, the fused deposition model printers, there's motors that pull the filament into the print head, but mainly we're talking about the actuators or motors that move the platform and the print head and all the other motion. We want motors that move consistently, very smoothly, without any type of buildup and friction, and we want them to move steadily. We don't want them to jump or accelerate or decelerate. Okay. And then finally, machine stiffness. We want a very stiff machine. If the 3D printer is flexible, then that flexibility is going to manifest itself in a not accurate and not repeatable print. Okay. So those are some factors affecting 3D printers, and specifically in terms of resolution and accuracy. All right. So moving back to vat photopolymerization, there's two possible part orientations that we can have during a vat photopolymerization building process. Okay. The first one we're going to look at is the bottom up building. Okay. In this build process, the platform is going to start at the bottom of the vat or reservoir of the photopolymer liquid, and the platform is going to move up as the layers are being solidified one by one. So the light source is going to be below the resin reservoir. All right. So you can see that in the below up, the magnified section right here. This is this type of process, build process, the bottom up building, is indicative of the DLP process and the clip process, both of which we'll talk about in more detail later. The other type of, well, here, let me stop here. The bottom up, this is kind of a example of the bottom up. So you can see down here in this example, we have the mirror, right? And the lasers that are shining onto this. Actually, we have some galvanometers down here as well. The laser is number 5. So the laser is shooting off of this. The galvanometers, really, remember, the galvanometers are mirrors that are moved accurately to provide the reflection, the desired reflection for the laser to trace out the shape on the build platform. And then we have a reflecting mirror right here. Okay, so that's an example of a bottom-up process. If we look down now at a top-down building process, in the top-down process, the light, of course, is going to be from the top now. The reservoir is going to, the build platform, I should say, is going to start at the top of the reservoir, and it's going to move down as the layers are solidified one by one. So the building is going to occur above the platform as opposed to below the platform in the bottom-up process. This kind of process is indicative of the SLA process, stereolithography process. Okay. And again, we can see an example here. So here we have the laser, right? And it's going through a couple of focusing lenses. And then here we have the, what they call the XY scanning mirror, but it's kind of the galvanometer as well. It's basically the mirror that is going to move to allow the laser to trace out each layer. All right. And then here's the build platform, and the build platform is going to start at the top, and it's, as the part grows, it's going to move down to keep the part completely submerged in the liquid, right? This part right here, number 1, is the sweeper. That's, remember I talked about the blade that moves across the top of the liquid just to make sure that there's no, disturbances or any residue up there to keep everything smooth. And so that's what the blade is, the sweeper right there. All right. And there's a couple of particularities about the bottom-up and top-down process. When you're building in the bottom-up process, or excuse me, when you're building in the top-down process, you want to build to minimize support. So you want to orient the part so that you have as little support material needed as possible. So you can see that in this case, they've oriented the part kind of flat or parallel to the build platform so that we have short-ish supports. Now, in the bottom-up process, we have a different issue that we have to watch. Okay, so you can imagine that this is kind of upside down. All right, so this image right here should really be turned upside down. I apologize for that. It was just a figure that they had in the book, but so this is building from the bottom up. But here, the issue that we really have to control for in the bottom up process is peeling or separation of the part from the platform as it's moving upwards. Okay. And so in order to minimize the chance of separation, or what we call, or what is called the peeling of the part, we want to minimize the cross section, because the cross section of the part, I should say, the cross section is, by minimizing the cross section, we're going to minimize the forces that are pulling on the part, and thereby minimizing the peeling or the separation that could occur during the build process. All right, let's look at a couple more figures. So we're gonna now focus on stereolithography, and then we'll switch to the DLP process and the clip process. But let's focus more intently right now on the stereolithography process. All right. So in a generalized process here, remember we have the build platform that's going to be starting at the top of the reservoir and moving down. So that's a top-down method. And we have the laser going through some focusing lenses, and it's striking the XY scanning mirror, also known as the galvanometers, okay, or galvanometer. And this is a mirror that's going to be moved with motors very, very precisely, so that and you can see it right here, so the laser is basically going to trace out the shape of each layer. All right. As each layer is solidified, the build platform is going to move down one layer in thickness. All right. The sweeper is going to sweep across the top of the reservoir just to make sure that there's nothing sticking out, no solidified material that's kind of sticking up, and it would cause problems. And then it's going to continue again with another layer. All right. Now, we'll watch a video here of the stereolithography process. All right. There's no sound in this, so I'll talk over it. Here you can see the laser. Let me just stop it right here. So you can see the laser up here, and it's shooting through some focusing lens and some mirrors to direct it into the right location. And then this mirror right here is the galvanometer. You can see it's attached to a servo. This might also be, it's hard for me to see, but this might also be a galvanometer. So it's going to be directing off that, and you can see it's going to be moving downward into the vat. All right, so let's continue this. And you can see it's tracing out the layers. Yes, in fact, that is another mirror. So we have the two mirrors that are going to help trace out. Remember, this is a vector scanning system. So what's being solidified is only the liquid polymer that's being hit by the laser. And of course, the laser can scan very quickly, but it's not as quick as the DLP process or the clip process. All right, and you can see as it moves, you can see the blade that was going. And now this is just the build platform moving upward to expose the finished part. You can see here, let me stop it. Whoops, let me get down to this. All right, and I'll stop it here. So you can see these are all supports which need to be removed, right? We need the supports to support the unsupported build material up here. So this is a fan blade. So these fan blades need to be supported as they're being built. So this scaffolding is the support material. It's the same material as the rest of the parts, but it's made in such a way that it's easily detachable. Okay. All right, now let's look at another video. I believe this one has sound, so I'll let it talk.
All 3D printing technologies create solid parts from 3D models layer by layer. Among them is SLA. SLA stands for Stereolithography, a 3D printing process that uses a UV laser to cure liquid resin into hardened plastic.
Now, I want to back that up a second here because it's very interesting that this, as I said, the top-down process is typically a stereolithography process, but notice that this is a bottom-up process. So it doesn't have to be, stereolithography does not have to be a top-down process, okay? So this is an example, and actually, this is similar to one of the machines that we have in our lab, which is a bottom-up process. All right, let me continue.
Plastic. Upside down, or inverted stereolithography, is the most common SLA system. Depending on the machine, resin is either poured into a tank by a user or dispensed automatically from a cartridge. At the beginning of the print, a build platform is lowered into the resin, leaving only a thin layer of liquid in between the platform and the bottom of the tank. Galvanometers direct the UV laser through a transparent window at the bottom of the resin tank, drawing a cross-section of the 3D model and selectively hardening the material. The print is built in consecutive layers, each less than 100 microns thick. When a layer is complete, part is peeled from the bottom of the tank, letting fresh resin flow beneath, and the platform is lowered once again. Originally developed in the 80s, SLA was confined to large industrial machines until recently. Today, desktop stereolithography offers affordable, high-resolution 3D printing that fits conveniently in your workspace. SLA allows for the use of a wide range of materials with diverse physical properties. Whether you're an engineer, product designer, sculptor, jeweler, or dentist, there's a material for your application. All 3D
product designer, sculptor.
Okay, so those are a couple of examples of stereolithography process, both the top-down and the bottom-up process. So, you can see a little bit more of how that works. Let's talk about some typical SLA characteristics. The accuracy, as I said, is one of the best in the entire additive manufacturing field. We're talking at least plus or minus 25 micrometers, or microns. Now, let me just say about these typical SLA characteristics. These numbers I took from data a couple of years ago, so 2018-ish. It is very likely that these numbers have been bested at this point. Because 3D printing and additive manufacturing is just so explosive right now in terms of a technology. So use these typical characteristics, as I'm saying, as kind of generalized numbers. There's going to be better numbers out there on different machines. Okay, so accuracy plus or minus 25 microns. Resolution as small as 6.35 microns, okay, which is tiny. That is very, very small. Layer thickness, right, that's in the Z direction, is anywhere from 125 microns to 50 microns. The build volume can be quite large, right? There are industrial vat photopolymerization or SLA printers that can print quite large. You're only constrained by the amount of resin that you can use, okay? So up to 1500 by 750 by 550 millimeters in cubic volume. The material, however, is still going to be photopolymers, thermosets, although there are a wide range of these types of photopolymers that have many different characteristics. And the application areas, because of the high resolution and the high accuracy, they're often used for conceptualization models where you really need finer details, prototypes, casting patterns, right? So these are some of the typical characteristics. They're often used for dental or medical models because of their high accuracy and high resolution. So here's a couple of examples here. So we have a tough, flexible material for simulating polypropylene. So you can see this. This looks like part to a car, like a vent for an air conditioner. Here we have USP grade that is medical grade water clear stereolithography for making this jaw, this lower jaw. Here we have some high temperature resistant for ceramic filled material. And then we have durable stiff stereolithography material with good optical clarity. This simulates polycarbonate. All right, so lots of options here. All right, so this is going to stop the first part of the lecture with stereolithography. We will pick up the second part of the lecture with a discussion on digital light processing.